Today we're very happy to have Roy Patterson from the Center for the Neural Basis of Hearing at Cambridge University. Roy has been, in my impression, a leading light in the hearing research business for a very long time. We've known each other for quite a while, and I could tell you some stories, but this is not a good time for that, I guess. So we'll let Roy tell his stories. Roy, take it away.
Thank you. It's a delight to be here. I think this microphone is working. Okay, well, I've given you a not quite knowing what the Google audience would be, I've given you a selection of titles. The topic is, there is size information in sound. You can tell the difference between a child and adult, and you need to normalize for that in order to communicate. So that's the first title. The second is my description of how the auditory system does this. It produces a scale shift covariant auditory image. And the auditory image is just like a visual image. If you open your eyes, you see an image. Similarly, if you just, when you wake up, you open your ears, and if there's sound there, your auditory system makes an image of it automatically. And it's the processing that goes from the sound to that initial image that I'm trying to characterize. And finally, for a speech community, making speech recognizers family friendly, I'm just referring to the fact that if you train a recognizer on a man, it won't even understand a woman, let alone a child. And it's the children that actually know how to make the technology work. So you really want the child to train the recognizer so that you can use it. And this is my idea of making recognizers family friendly. Okay. There are a lot of people involved in this research, so I'm representing quite a large group of people doing research. These up here are the postdocs that are currently in my lab, all of them working on this. Two of them have just got good jobs elsewhere, but we still keep them on the list because they're working with us. And we have 4 students, one of whom is here, Tom Walters. We also have 2 well-known Japanese colleagues who are intimately involved. Hideki Kawahara, the father of the vocoder straight, which you're going to hear about, and Toshio Orino, who works with me on all of the wavelets and Mellon transform and size stuff. So you may not know them, but you may want to. So the overview is that there is size information in communication sounds, in speech, music, and animal calls. Humans can extract the content of the communication without being confused about the size of the source. And humans can extract the size information without being confused by the content. Auditory perception is amazingly robust to variability in communication sounds, and these size changes change the sound a lot. Machine recognition systems are not robust to size variability, even when it's a single speaker in clean speech. Okay? So, how does the auditory system do it, and can we capture it in algorithms and make them useful? Okay, so I'm going to start with the size information, what you need to know about the size information in communication sounds, and how people perceive it. Then I'm going to tell you about, we've developed a little recognizer to equate machines and humans on a certain task, so that we can demonstrate the robustness of humans and to give us a measure as to how the machines are doing and when they're improving. And then we say, okay, can this auditory representation be used to produce better features for the recognizer? And in the end, I'm going to tell you that it looks promising. Size information and communication sounds. Okay. The sounds that animals use to communicate at a distance, to declare their territories, and to attract mates, the important stuff in animals' lives, are typically pulse resonance sounds, which means that the animal finds some way of producing a pulse, typically by banging 2 hard parts together. The pulse marks the start of the communication. The energy goes into the body of the animal, and that object then resonates, and that resonance is attached to the back of the pulse, and that resonance tells you about the structure and the size of the animal. And it's that simple trick that the animals are using. Okay, so an animal of interest to us, the human, the information and speech sounds. You have vocal cords at the bottom of your throat. They vibrate and interrupt by interrupting the airflow from the lungs and produce a stream of pulses. Those pulses excite resonances in the vocal tract, and the shape of the vocal tract, the place where you put your tongue, determines the resonance and thus the vowel type. And, but in addition, vocal tract length determines the rate at which those resonances run. And this is the new variable that I need to draw your attention to. So, if you have a large person with a long vocal tract, and then you have a small person with a short vocal tract, they can actually say vowels with the same pitch, and they can put the vocal tract in the same shape, so that you hear the large person and the small person saying the same thing, but you can still tell which is the big one and which is the small one, because the difference in vocal tract length produces a difference in the rate at which the resonances behind the pulse run. So, here's an example. In this slide, there are 6 copies of the vowel ah, and over here, and it's always the vowel ah, and you can tell that because the resonance after the pulse is the same shape in all 6 slides, all 6 waves. Over here, the pulses come at an increasing rate. So over here we have ah, ah, ah. Can we turn that up a touch? Nope, not that way. Ah, ah, ah. So that's a pure pitch change, and that's very simple. I can do that. Ah, ah, ah. Over here, notice that the pulses come at the same rate in all 3 of these. So the voice pitch is the same over here. And the vowel is the same. It's the same shape. But over here, as we go down, the resonance runs faster. The peaks occur faster, okay? And here you get ah, ah, ah. And that is the sound of a pure vocal tract length change. Ah, ah, ah. I can't do that one. Ah, ah, ah. That's the dimension we need to go after. Okay. Now, animals typically, all modern animals, communicate with what we call communication syllables. So animals put out their pulses in bursts, and each of the pulses carries the resonance behind it, so you get lots of copies of the resonance in a pulse resonance sound. So here's a human communicating with pulse resonance sound. Ma, ma. And here's a macaque. And another very successful communicator. And this is a fish. And I include the fish because they probably started doing this as much as 500 million years ago. And they do it with very different mechanisms, but they're using the same trick, pulses with resonances attached. They always seem to be at about a ½ second long as well. All right. So that's pulse resonance communication. So what you need to know about communication sounds is that in the communication sounds at the syllable level, I mean, there are larger issues. There's syntax and semantics and prosody. But just down at the level of the individual sound, the syllable, there are 3 kinds of important information in communication. There's the resonance shape, and that's the message. There's the glottal pulse rate, that's the pitch. And there was the resonance scale, which tells you how big the speaker was. So in animals, they all grow, and all animals evolution invariably uses parts of the body that are already existing to make the sounds. In our case, it uses the tubes from the nose and mouth to the lungs and the stomach. And as you grow up, those tubes have to get longer to connect you to the outside world. And so there must be size information in animal sounds, and this is true of all animals. And so it's an important problem for animals to be able to generalize across sounds and recognize that a new sound, which is physically different, is actually just the same message being carried on by a source, produced by a source that's a smaller size.
How large a cricket is by the sound that it makes?
Oh, you are very... So the bush cricket is the one animal that has learned to make a sinusoid. And it makes a 4 kilohertz sinusoid with a patch of its wing, and it doesn't communicate till it's full-size adult. So it's one animal that has very little size information. Pick another animal.
I'm really curious about minor birds because I don't think they produce their sound. Rather than hitting a vocal tract with a bunch of pulses and varying its shape.
Yeah, no, they have 2 syrinxes. They have one on each side. But if we just take one at a time, then the syrinx does have a vibrating source that interrupts the airflow.
But do they have any continuously changing resonance, or are they continuously varying the pitch itself?
Repeat the question.
Oh, what about the minor bird? So the first point is that birds are much more exotic than us. They have a voice box in each branchium. And they actually, the songbirds have a brain that allows them to play one, play the other, or play them as a pair. So all of that aside, in the syrinx is a flapping membrane that is producing pulses. And those pulses are exciting the vocal tract. Now, in the birds, you have 3 sections of the vocal tract, just above the syrinx, and then you have the throat, and then you have the mouth. But in birds, the mouth often includes the bill. So it's complicated, but it is the same kind of sound.
It represented to me in conversation once that LPC wouldn't work on minor bird speech because it's varying the pitch period continuously instead of varying the vocal tract shape. But that may be entirely mistaken.
I think the issue is just, I mean, there are more variables there. I'm just giving you 3 of the simple ones. Yeah. And these apply, but then there are more. We had a student project on it, but I'm trying to remember it, but I can't. Okay. So this is true of human speech, that they use pulse resonance sounds, and it has this 3 kinds of information at the syllable level. It's true of animal calls, mammals, birds, fish, frogs. It's true of grasshoppers, actually, and shrimp. It's true of most musical instruments. Most musical instruments, when you look, have pulsive excitation and that resonates in the body of the instruments. So it appears that certainly in the sustained toned instruments of the orchestra, that we have chosen sound makers for which we already have an analysis mechanism. But that's another topic. And of course, engines have explosive pulsive excitation. And as you know, any good mechanic will listen to the car for a while before he takes it apart, because you can probably tell a fair bit about what's wrong just by listening. All right, these stand in contrast to the inanimate sounds produced by turbulent air and turbulent water in the natural environment. Wind in the trees, rain on the roof, waterfalls and such. And maybe 500 million years ago, animals started using pulse resonance sounds because they stood out against the natural background. But that's another story, another long story. All right. So that's all you need to know about the size information in communication sounds. As you get bigger, your pulse rate will go down because your vocal cords get longer and more massive. And as you get bigger, the resonances will ring slower because they have more mass, essentially. And this is just a very general principle in sound production. Okay, now, what about the perception of communication sounds? I've said we're robust. I just want to draw your attention to a few experiments that we've put in the literature to prove this. All right. So what I'm going to present you here, we now have, thanks to Kawahara-san and Arino-san, we have a computer application that can take my recorded speech, take it apart, cycle by cycle, and then change the glottal pulse rate and change the vocal tract length and resynthesize. And this allows us to do nice control experiments where we have very good control of glottal pulse rate and vocal tract length while preserving all of my individual speaker characteristics. If you want to do experiments, this is the tool. So here, most of the slides I'm going to show you have glottal pulse rate on the abscissa and vocal tract length or some other measure of resonator size on the ordinate. And here, the pitch is going up and the vocal tract length is going down. So I'm going to present you sets of 3 speakers who differ in pitch and vocal tract length. And each one of them is going to say 3 syllables. And your task is to say whether the 3 speakers are saying the same 3 syllables. Okay? So listen carefully.
Mo, pi, fa.
Mo, pi, fa. Mo, pi, fa.
Mo, pi, fa.
Mo, pi, fa. Mo, pi, fa.
It's trivial. The change in size from a young boy to a teenager to a large adult is absolutely trivial for you. So you may think you've learned this because you have a lot of experience with children and teenagers and adults. But I have some other speakers here which have combinations of glottal pulse rate and vocal tract length which you are very unlikely to have ever heard. Okay? A very short vocal tract with a low pitch and a very long vocal tract with a high pitch, same person in the middle. Try this one.
Woo, di, ha.
Woo, dee, ha. Woo, dee, ha.
Trivial.
Woo, di, ha.
Woo, dee, ha. Woo, dee, ha.
And we can do it with a fixed pitch and a changing vocal tract length.
Re, ku, sa.
Re, ku, sa. Re, ku, sa.
So that's the size component of the perception that is specific to vocal tract length. And there's a component specific to pitch.
Na, te, zi. Na, te, zi. Na, te, zi.
However, the point is you are amazingly robust to this. So that's the audio demo, and you're also very good at telling what the size of the speaker is. I'll come back to the recognition problem in a minute. Or, well, maybe I'll do it right now. Okay. So you're robust to changes in size. We took the 5 vowels, A, A, E, O, and U, spoken by me, and we used this magic program straight to scale the glottal pulse rate all the way from my normal 110, all the way up to 640, and down to 10 hertz, below the lower limit of pitch, where you're hearing individual cycles. And we scaled the size from my size to double my size and half my size, which is an enormous range. And we said to the person on each trial, here's a vowel. Which of the 5 vowels is the person saying? And they had to choose one of 5, okay? 5 alternative forced choice tasks. Now let me just point out, these are the mean data. And this ellipse here shows you the combinations of vocal tract length and pitch of 99% of the people that you have ever heard. Their combinations are all here. So small children are here, and women are here, and men are here, and very large men are here. So they're all in there. So when we go beyond that, you really have not heard speakers of this type before. So how do people do? Well, this is just a very simple task for them. The 50% chance, which is D prime, a statistical measure of the fact that you can do this reliably, is this black line, which is barely in the picture. And for all of the yellow and orange and red, you can do this task well, way above chance. And I think this dark color is about 95%. And you can do it all the way down to below the lower limit of pitch. You're just amazingly robust to changes in size. Now, so that's to say that you can get the information about the message independent of the size of the source. At the same time, you're peeling off the size information in a useful way. Because, sorry? Sorry. Okay. So we took the same set of vowels, and they vary in glottal pulse rate and vocal tract length. And we played single vowels to people and said, how big is the speaker? From very small, 1, to very large, 7. People are consistent. If you give them a low glottal pulse rate and a long vocal tract, they say that's a very large person. And if you give them a high glottal pulse rate and a short vocal tract, they reliably say that's a very small person. The 2 dimensions both affect your perception of size in that both of these come down, and they interact. The surface is not simply a plane. So as you go up in pitch, it's fairly linear in log glottal pulse rate. But over for vocal tract length, in the range that you have experience with, it's fairly flat. Then it goes quite steep. When you go to the normal range, suddenly people start to sound really quite small quite quickly. But it's a stable source. Okay, and another experiment to make it more speech-like, we produced a syllable database. And this syllable has consonant-vowel syllables, and it has vowel-consonant syllables. And the consonants are the 3 main groups: sonorants, stops, and fricatives, 6 of each. And the 5 cardinal vowels, a, e, o, and u. And that gives us 180 syllables plus 5 vowels. And we use that to do some discrimination experiments, which I'll tell you about in a minute. So if you take normal recorded syllables and just play a sequence of them, it will sound irregular. And so these syllables have also been what we call P-centered, to basically focused on the vowel onset, which when you play them in sequences makes the rhythm sound even. So then we can draw randomly from this database and get sequences like
Me, ein, ka, it, so, us.
Me, ein, ka, it, so, us.
All right. And so straight produces very, very high quality vocoding. And we run experiments like this. So we do experiments in psychophysics, and we have to be very careful that there aren't any extraneous cues that you can use to do the task. So if we just took 2 vowels and said, which of these speakers is larger? As a matter of fact, if you're using a log frequency scale and you have 3 formants, as the person gets larger, that spectrum moves as a unit towards the origin. So if you could just glom onto one of the spectral peaks and follow that and compare that spectral peak between the 2 intervals, you'd be able to do this task. The task is, sorry, we're going to present 2 intervals. You have to say which speaker is larger. So we make the spectral cues. We scramble the spectral cues very badly. And we do that by choosing a selection of syllables at random from that database, 4 of them. And we present those in interval 1. And we give them a pitch contour that is reasonable for speech, and the pitch is also moving the spectral components all over the place. And then in the second interval, we select 4 syllables again at random, and we give it a different pitch contour. So there really isn't any pitch cue that you could, or spectral cue that you could carry and compare between these 2 intervals. However, in the first interval, all of the syllables were constructed with the same vocal tract length. And in the second interval, all of the syllables were constructed with that vocal tract length plus a bit or minus a bit. And you have to say which one was larger. So, ready?
Ma, et, ku,
Say, te, wa.
Ma, et, ku,
Say, te, wa.
Which interval had the smaller speaker? One person got it wrong, but I won't say who.
Ma, et, ku,
Say, te, wa.
Okay, that's about a 10% change in vocal tract length, and after 2 minutes training, most people are close to 100% on that. It's a very natural thing. You just bring people in and say, the speakers are different size, tell me which one's smaller. And we do that experiment, and we do it for five different starting points: large male, small child, castrato, and dwarf, the same ones I've been using all along. Okay? So now these are 5 psychometric functions for those positions, and you start off here with a certain vocal tract length, and you compare it to vocal tract lengths that are longer. And as soon as they're a bit longer, then you go to 100% on which one's smaller. And if we reduce the vocal tract size, then you go to 0% on the smaller one because you're choosing the larger one, or you're inverting the choice. Anyway, the point is that as you change the vocal tract length away from the starting point, people rapidly can do this task reliably. This is true for all 5 of these speakers. It doesn't seem to matter where you start. And the slope of the psychometric function is about the same in all cases. So we can create a statistic that psychologists call the just noticeable difference. That is, the difference you have to make on a dimension for it to be reliably detectable. And we do that by saying, how much vocal tract length do you need to raise the percent correct from 50 to 75? All right, and that's statistically well defined as a d prime of 1. Well, it's a little more than d prime of 1. So if we do that, what we find, and now I'm showing you the data for all 6 of the different kinds of consonant vowel and vowel consonant syllables separately, but it doesn't really matter, but that's just why there are 6 points on each of these. And this line, this fixed line is 5% in each of these data plots. And what you can see is that for the small male, the large male, and the castrato, with the longer vocal tracts, these 3, you need about a 4% change in vocal tract length in order to reliably tell whether the speaker is larger or smaller. And for the shorter vocal tracts, you need 6 or 7%. But, on average, you need a 5% change in the size of the resonators, or the size of the, I should have told you, vocal tract length is very highly correlated with your height. So when a 5% change in height will produce a 5% change in vocal tract length, and it's the acoustic scale of the vocal tract that you're detecting. Now, why is that important? That means that, so this supports the idea that you have access to the acoustic scale dimension in the brain, and you treat it like a dimension. The just noticeable difference for loudness of a sound is 10%, 10 or 11%. The just noticeable difference for the brightness of a diffuse light is 14%. The just noticeable difference for the duration of a sound is 10 or 11%. So 5% JND is a very good JND for perception. It's not as good as pitch, and it's not as good as visual acuity, but it's a very good JND. You can also do these experiments with musical instruments. We published a paper in Jazz on the horns, strings, woodwinds, and voice, but I don't really have time for that today. Okay, so that's the first point. So I've told you about the form of the size information in communication sounds, and I've told you about the perception. We're amazingly robust. We seem to be able to take these sounds apart. And why is that surprising? Well, let's go back to these sounds and look at their magnitude spectra. So if I take the Fourier transform with a windowed Fourier transform and integrate it and produce a spectrogram, and these are slices of the spectrogram, or magnitude spectra. And when you change the pitch, you change all of the frequency components and all of their amplitudes. I mean, you just move them all over the place. And when you change the vocal tract length. Now, it is actually the case that if you really have a fixed pitch when you do that, it would be the same frequency components in your spectrum, because they would all be harmonics of one fundamental, but all of their amplitudes change. And normally, you have a combination of these two, so the spectral components are just moving around in a dizzying way. But there's something about the pattern of them that the system can detect. Okay, so really they're being scaled, but scaled in 2 dimensions, glottal pulse rate and vocal tract length. And recognizers have trouble with this. Now, to illustrate this, humans find it hard to believe. Humans believe in recognizers, and they think if you train it on one person, it'll be able to recognize another because we can. So, but we needed to test that. So we took the syllable database, and we did an experiment with humans. That is, we took the syllables, and we produced people with all of these different combinations of glottal pulse rate and vocal tract length. Okay? Loads 56 people. And we trained humans on, we trained people on the one at the very center of this blue spot and 8 others in this blue spot. Okay? But basically, we trained them on people of one size. And we had to train the humans. Training for the humans means learning to use this GUI, where we would present them a syllable, and they had to tell us which syllable had been presented, okay? And they have to learn the funny way in which we're going to use the syllables ma, me, me, mo, mu. And they have to learn to find all the positions, and that's basically what they're doing, is learning to use the GUI. Sorry. On this. And then, without any further ado or any further training, this is where those voices are in the normal space. So here's 99% of the men you've ever heard, 99% of the women, and 99% of the children. This is where the voices are that we were using. And we just, all of a sudden, started presenting, instead of the person at the center, we presented people at the ends of these spokes. So suddenly, the size of the person is changing dramatically on every trial at random. And it makes almost no difference to humans. Now, that doesn't surprise you, but I'm saying this is our measure of robustness. You can train on one point, test on any points in the space, and it hardly makes any difference. It is the case that the end of this spoke, 3 and 7, which are the most unusual voices, your performance is a touch worse. But that really is a small effect, and this is 20 observers with a very large number of trials. All right, keep that in mind. That doesn't surprise you, but maybe it should. We took an HMM recognizer, a hidden Markov model recognizer, and you need about 3 emitting stages for recognition of syllables. And we used MFCC features. So this is pretty much an industry standard kind of recognizer set up to work on our syllable database. Clean speech, single syllables. And we trained the recognizer on 9 voices in this blue region here. And when the recognizer was trained, so that it was producing, this is error rate, so that it was producing an error rate of 0 on the syllables that it had been trained on, we then started to change the vocal tract length on the recognizer, and immediately, as you go away in vocal tract length, the error rate rises rapidly and to a disastrous level. Okay? So recognizers are not robust to extrapolation. If you take this same recognizer and train it on half of those voices from all over that region, and then test it, it does very well. It does 95% if it has seen all of the data that it has to work on. So it can interpolate between voices that it has learned from. It can get the one in the middle between them, but it isn't any good at extrapolation. And as you saw in our recognition experiments, humans can extrapolate way beyond anything they've ever heard. All right. So the auditory system appears to adapt to the pulse rate and the acoustic scale of communication sounds automatically, as if we have a transform. So what I'm proposing is that you have a normalizing transform in the system before you try and do the recognition. And the processing appears to produce a speaker size invariant representation of the message, which is very convenient. So how might the auditory system do this? All right. To explain this, so what I'm going to do is take 4 sounds and take them through several stages of the auditory system to see if we can get them all to be the same in the sense of the message being the same. And I'm going to start, and these are all 2-formant vowels, and in all cases, the formants are just damped resonances, and they are all scaled versions of one another. So it's exactly the same object in different sizes. And I'm going to start with a long vocal tract and a low pitch here, and then I got one where you have a long vocal tract still, but you have a higher pitch, in fact an octave higher, and then a short vocal tract and a low pitch. So the pitch is the pulse rate, and the vocal tract length is the resonance rate, so this one rings faster than this one. And then finally the combination of short vocal tract and high pitch. So I've got a 2x2 in which both of these crucial dimensions are varying. Now, I take those 4 sounds and I put them into an auditory model. This is my favorite gamma-tone auditory filter bank, but you can use almost any filter bank to do this, or any wavelet transform. The auditory system is really performing a wavelet transform in which the kernel scales with the carrier. All right. So down here, this triangular shape here is what you get when a glottal pulse strikes a simple resonator. It rings for a while, okay? And here is the second formant, and it rings for a while. It's at a higher frequency. It happens to ring for exactly the same number of cycles, but since you're at a higher frequency, the cycles go by faster, so it dies away quicker, all right? And that's the form of, this is the form of a size change. In this representation, the object moves up and shrinks. So if we move to, if we shorten the vocal tract, and we're on a logarithmic frequency scale here, logarithmic frequency or acoustic scale, then the shorter vocal tract transforms both of the formants proportionately, so they move up as a pair on this scale, and they both shrink. Again, they have the same number of cycles, but you're using a different acoustic scale to represent them, so their shape changes. They are not size invariant in this representation. So what can you do? What could you do to fix this? Well, the obvious thing is to just change the frequency dimension so that you pull the cycles out, so that you got the same number of cycles in each case. So I just want to take this one and pull it out to there. And for these up here, I want to pull them to the same point, because then I know they've got the same number of cycles in them. And the question is, can you do that in general? And the answer is yes, mathematically you can. What you have to do is take your time dimension, and in each channel separately, multiply time times the center frequency of the channel. And frequency is increasing as we go up. So as we go up, we're steadily expanding the time dimension. And if we do that to this representation, we get this representation. This is an expanding neural activity pattern. And I probably should have said, this is the kind of representation we think you have at the output of the cochlea flowing up the auditory nerve to the cochlear nucleus. We call it a neural activity pattern. And here's an expanded neural activity pattern, as if the auditory system treated time differently in each channel. And you can see that that has successfully converted these 2 resonances, which we know are the same kind, into the same shape in this space. And it's also converted the ones in the shorter vocal tract into the same pattern. And pitch doesn't matter to this representation because this is really the ringing of the vocal tract, and it doesn't matter what the period of the vocal cords is, unless the period of the glottal pulse period gets to be shorter than the ringing of the formant. And actually, in speech, that does occur. But that's a separate problem, but I'm not trying to hide it. Okay. So this is very nice. We now have a representation in which the message is the same for all 4 of our different sounds. The only problem is this representation is not time shift covariant. That is, when we get to the second cycle, we find that our expansion has messed it up. First of all, it's put the glottal pulse line, it's twisted the glottal pulse, it's shifted the glottal pulse line over. And secondly, this is a log, so the dimension is the log of the number of cycles of the impulse response. And because of the log, it's compressed it in the second cycle, so successive cycles don't appear in the same form, and that's not very good. But what we actually think is that the auditory system restarts time on each new glottal pulse. So when it gets here, it really flips back and puts the next cycle. It's really measuring time from each glottal pulse. And as long as it does that, then it will find all the glottal cycles. There's not much change between successive cycles, and it's going to plot them on top of each other. And we call that strobe temporal integration. And you have to do that a little sooner if the pitch is higher, but it's not really a problem. So if you do that, you then get a representation where the cycles are all falling on top of each other as long as the sound is stationary. And this we call the scale shift covariant auditory image. It's a nice stable image. It's an image in which change occurs if you hear a change, and change does not occur if you don't hear a change, which is not true of neural activity patterns. So in this image, what happens? Well, you have your 2 formants, and they are now the same size. And you can see that it's the same formant. And if the size of the person changes, this pattern just moves vertically as a block. So it's scale shift covariant because in the representation, you still have the message and you have the size information, and they are both there. They co-vary. So you have both kinds of information still in there. But now you've got them in a nice orthogonal form because that pattern just moves as a block when you change the size. If you change the pitch, nothing happens to the message. It just stays where it was. What happens when you change the pitch is that the terminating line for the glottal period changes. So actually, if you have a noise, then you can have activity in throughout this entire image. As soon as the sound becomes periodic in the way that speech does with glottal pulses, then you can no longer have information down here. So when a periodic sound comes on, suddenly you lose everything below this diagonal, and the diagonal tells you the pitch. So now you have the 3 elements: vocal tract length, glottal pulse rate, and the message separated and represented in an orthogonal form. All right? And this, I think, and a number of people do, think that this representation of what you hear is a better representation because here the message is awe and it doesn't change. The fact that a child chooses to say it and an adult chooses to say it, that doesn't matter. It's the same message. And whether they're a child or an adult is determined by where the pattern appears and where this terminating line is. Okay. So, can we make use of this? So you remember that we trained the HMM recognizer on a syllable database, and if we of one speaker, and when we changed the size, it had a problem. What happens if we take features from the scale shift covariant auditory image? So if we make spectral profiles, just add across the auditory image, you get this green line in here in behind. So to that, knowing that what we were looking for is 3 formants, we fitted 3 Gaussians to the spectra as they came along. And we used those features instead of MFCCs for the recognizer. And we did one more thing. We know that this set of 3 formants will move back and forth when size changes. So we did what speech people from Katayama and Font Forward have told us, use formant ratios. It's the formant ratio on a log scale that is fixed. So we gave it difference of the Gaussians, we gave it the heights, and in total, this gives you somewhat fewer features than the MFC features that you would normally use, like about a dozen. And in this case, when we take the same recognizer operating on the same database and have it work on mixture of Gaussian auditory image profiles, then when you train it on this speaker here, and then you change the vocal tract length, the error rate does go up a little as you move away from the training vocal tract length, but it stays at a reasonable rate in comparison to going up to 100% error. All right? So we think that these features are more invariant and they capture the information in a more useful way. And from the auditory point of view, we argue that it's a better representation of how you hear. So, in summary, there's size information in communication sounds. And I told you about the perception of communication sounds. Humans are very robust. Machines are not when you develop a measure that allows you to compare them. And I've shown you how we can take auditory models and extend them to produce a scale shift covariant representation, and that does indeed help recognition in this environment. So currently, to finish off, the databases for recognizers currently have thousands of hours of information in them from many, many speakers. And they take thousands of hours to train because there's so much information in the database to make them robust. And we think what's the problem there is you're actually having to find enough different speakers so that the recognizer can hear every syllable you want it to recognize with every different combination of glottal pulse rate and vocal tract length. So, and we don't think the auditory system has to do that. And this is the way to handle it. Thank you.
What would you expect the performance of a conventional recognizer like that could be benchmarked against? If it was trained with a single voice, and that voice extended by this parameter method.
Yes.
Use an extended training set that way rather than using the other recognizer. How would it stack up?
Exactly. The answer is we don't know. The prediction is obviously, I'm sorry, repeat the question. What would happen in your database? You make a database of a large number of speakers because you want your recognizer to be speaker independent. What if you took all those speakers and then scaled their speech to a large number of different combinations of glottal pulse rate and vocal tract length? And we think that's a great idea, and we haven't yet done it. You're actually seeing our research up to about a month ago. So that is exactly what we want to do, and we've been looking for some collaborators to do it with. So what our prediction has to be that you can reduce the number of speakers in your database and get higher recognition at the same time. And it should take less time to train the recognizer. So we have a strong hypothesis, and we're dying to know whether it's right.
So your representation that you did recognition on essentially comes down to detecting formants and using their ratios and a few other parameters. Do you need your auditory image as a way to get to that, or do other kinds of formant detection systems do as well?
And the answer is we don't yet know. Let's see if I can find. So this was a quick thing to do that everyone would understand, was to take the spectral profiles of this image. You know what I want to do. I've got another slide here somewhere. So these are those same scale shift covariant auditory images tarted up to publish in a trendy journal. But these are the same patterns you saw before with the same terminator. The thing is, on this slide, I've actually plotted the profiles so that you can see that these are the spectral ones that we use to find formants. Down here is a temporal profile. The temporal profile is actually scale shift invariant. And so where we expect to make some more progress is to use this one to constrain the syllable search. It appears to contain information like the difference between front vowels and back vowels. So the answer to your question, do you need to use the two-dimensional image? We haven't proven it yet, but we think that the information in this temporal profile, which you don't have in a spectrogram, will also be useful. We have to figure out how to bring this information in the temporal profile together with the information in the spectral profile. But the answer to the question is we don't yet know.
I was going to ask if these slides are online.
They will be. I mean, we can leave you a copy to go with the talk if you like. Yeah. Thank you very much.